In this section, we're going to be connecting the first and second derivative with the graph of f. So this could look at a few things. It could be looking at local extrema. It could be looking at something called concavity, which is talking about how it curves, and then also the points of inflection. So we've already looked at finding extrema by looking at critical points. Remember, this is where f prime is either equal to 0 or does not exist. And but we noticed that extrema are not always found at a critical point, because remember, sometimes if we're increasing and then increasing again, we don't have a maximum or a minimum there. Or here we're decreasing and then decreasing, so again we don't have a maximum. But if we are increasing and then decreasing, so basically we have a change in sign from positive to negative of our derivative, we know that we have a maximum. So if we want to find local extrema, our first derivative test is basically looking for a sign change. Okay, now we're going to find where the sign could change based on looking at the critical points. But the critical points, again, do not guarantee a maximum or minimum. We want to look at the sign change. So if I'm changing from positive to negative, we know that we have a local maximum. Notice we don't need to have, again, a zero slope there. We could have a corner or a cusp. Same thing with a local minimum, changing from negative to positive, so decreasing to positive, and we know we have a minimum. Now we do need to check, because if I also am going from positive to positive, there's no change, therefore there's no maximum or minimum. Again, negative to negative, no sign change, and there's no maximum or minimum. We should also remember to check endpoints, and then for a left endpoint, if we're decreasing after that endpoint, it's going to be a maximum. If we're increasing after that, so the sign of f prime is positive, then it's going to be a minimum. Same thing with the right endpoint. Since I decreased to get there, it must be a minimum, and if I had to increase to get there, it would be a maximum. So using the first derivative test, we're going to start with our function and find the derivative. We then take that derivative and set it equal to 0. Now we also notice that there is nowhere that it does not exist. It's continuous. And so we end up with x squared is equal to 12 over 3, or x squared is equal to 4, x is equal to plus or minus 2. So those are our only possible values. Now we're going to do this using a table like this and consider f prime of x. Now our only critical points are at negative 2 and at 2. And so if my derivative is 0 here, we look at what's happening within these intervals. So if I choose 0 and plug it into my derivative right here, then between here I'm going to get a negative number, and then on either side it's going to be positive. That's telling me that I am increasing and then decreasing and then increasing again, telling me that x equals 2 is a local max, and x equals positive 2 will be a local minimum. For this one, it's going to take a little more work, because for this one we'll also take the derivative. We'll start with g prime of x. We'll have to use the product rule for this. So the derivative of the first would be 2x times e to the x plus e to the x. Now we can notice we can factor out that e to the x, leaving us with 2x plus x squared minus 3. So if I'm going to set this derivative equal to 0, notice I don't have to worry about e to the x. We should remember that e to the x is never negative, it's never equal to 0, it's always positive, and so really the only factors I have to look at are this x squared plus 2x minus 3. We can factor that to get minus 1 and plus 3, and so those changes are going to happen at x equals negative 3 and 1. We should consider those values then as though we don't have a graph. We could probably see it by looking at this graph, but if we didn't have that, we wouldn't actually need it. We can just plug in the 3 and the 1 and look at this table of values. Now also, since we have to justify our answers with calculus, we're not allowed to just look at the graph and say what's happening in an algebraic problem like this. So we plug in values between negative 3 and 1, back to our derivative here. Really, since this is always positive, we could even just look at this part, or even better yet, look at this part. And so if we're greater than 1, we're going to get positive values on each part. If we are less than negative 3, we're going to get a negative times a negative, which will make it positive, and then over here we're going to get a negative value. This tells us that we're increasing and then decreasing, which is telling us we have a maximum at x equals negative 3, and we have a minimum at x equals 1. The next key idea is concavity. And we talk about concave up when we're curving up, or concave down when we're curving down. Now we might only have a part of that curve, like could be just the beginning part, or the ending part will also be curving up. Basically we can define this by what the y prime is doing. So we say that it's concave up, or curving upward, if the slope is increasing. So you notice these lower values have a smaller slope, and as we move to the right, the slope is getting steeper. So we're curving up. We say it's concave up. For the part that's concave down, we notice that these slopes are decreasing. So we're starting with a steep slope, and then we're getting to a smaller and smaller slope of our tangent line. So we say that we are concave up anywhere where our second derivative is positive, and we're concave down anywhere where that second derivative is negative. So if I want to find the concavity of this, we're going to do kind of what we did with first derivatives, where we'll look at the zeros here. But first of all, this is my original function. So first we'll take the first derivative, which gives me 2x, and then look at the second derivative, which gives us a value of 2. Now notice that there are no changes here. There's no point in setting this equal to 0. This is always greater than 0. It's always positive, which tells us that this is always concave up. In the next problem, we want to find the concavity for this function, y equals 3 plus sine of x. So again, we'll take our derivatives, which will give us first a cosine of x, and then our second derivative, which will give us a negative sine of x. Now we only want to know about this on this particular interval, otherwise it would just keep cycling. And so we would, so to find the concavity, let's set this equal to 0. Now on the interval from 0 to 2 pi, the sine of x is going to be equal to 0 at 0, pi, and 2 pi. So if we want to find out where it's concave up or down, we're going to consider the values of x at, first of all, our starting point of 0, our ending point of 2 pi, and then this point in the middle, pi. Those all give us values of 0, so those are the only places where we could get a change in direction. So if I plug in a value between 0 to pi, a negative sine of x, okay, because we're looking at our second derivative here, we plug in any value between there, we're always going to get a negative value. Plug in from here to here, we'll always get a positive value. Okay, now this red then is the graph of our second derivative, where this is the graph of our original function. We can see again negative values and then positive values. So these negative values tell me that from 0 to pi we are concave down, and from pi to 2 pi we are concave up. We can see this on our graph, and notice that there's a change in concavity here at pi, but we are curving down everywhere before that and curving up everywhere after that. Now that point where we changed in that last graph there, where it changes from concave down to up, is called a point of inflection. So anywhere where the concavity changes would be called a point of inflection. Now this point of inflection is going to happen where we get a sign change. So let's look at this one here. If we have y equals e to the negative x squared, take our first derivative. So e would be e to the negative x squared, but times the derivative of that exponent. And then our second derivative, we would need to use the product rule. So the derivative of the first times the second plus the first times the derivative of the second. Again, notice that this e to the x squared is going to factor out, leaving us with here 4x squared minus 2. So if we want to set this equal to 0, notice that e is never going to be equal to 0, so we'll only be looking at 4x squared minus 2 and setting that equal to 0, leaving us with plus or minus the square root of 1/2. So looking at these values here, square roots of negative square root of 1/2 and the square root of 1/2, these are where our second derivative our second derivative is equal to 0. We look at what's happening between those. So again, we really only need to look at this part here. If I'm at 0, that's going to be negative, and then on either side it's going to be positive. And so we can see the concavity here, that from our square root, negative square root of 1/2 to positive square root of 1/2, since it's negative, we're concave down on that interval. Anything after that is concave up. Anything before that is also concave up. This guarantees then for us that both of those are points of inflection since we have a change in sign in our second derivative.